Hello. This week we're going to be looking at some applications of eigenvalues and eigenvectors, and today we'll look at the example of ranking sports teams. Here I've taken a little league. It's got 6 teams which have rather unimaginatively been called A, B, C, D, E and F, and I've recorded here what happened when they played. Now they didn't have time to play all the games, so for example team A beat B, E and F. But if we look down, the team B beat F, team C beat team A and team F. I'm just recording a 1 for a win and a 0 either for a loss or for not played. 3 of the teams played 5 games and 3 of the teams played 3 games. And the question now is, which is the best team and what is the overall rankings of the teams? So team A and E, they each won 3. They could argue that they're the best. But then team A might say, well, yes, but I beat E, therefore I'm better than you. And you can imagine that the arguments could just go on and on forever. In addition to which, team A beat team F, F beat D, and D beat A. So there's no clearly superior team that dominates all the others, and that will almost always be the case in a well-met league. So can we do a more mathematical approach? Using eigenvalues and eigenvectors, you may not be surprised to hear. This issue with ranking teams, it does actually come up in real life. In the United States, the Western US College Basketball League, I think it's got something like 110, 120 teams. They don't have nearly enough time in their year to play that many games because they're all university students. Maybe they played 12 games each. You can imagine it would be very difficult to tell which was the best team, and there could be a lot of arguments. So we've got that matrix. We recorded all the data into a 6x6 matrix. And the idea which lets us go forward is to suppose I want to know how strong each team is in a numerical number. I'm going to call Sj the strength of team J. And I'm going to suppose that if I beat a strong team, that counts more than beating a weak team. That seems to make sense. And beating a team of strength S will contribute an amount proportional to S to my own strength. I don't know what my strength is yet. I'm going to get a system of equations. So what do we know? Well, have a look at team A here. They beat B, E, and F. So the strength of team A must be proportional to the strength of B plus the strength of E plus the strength of F. So that means the sum from j equals 1 to 6 of aij times sj must be proportional to the strength of team I. That's my model for how the strengths are going to be apportioned. What is the constant of proportionality? I don't know yet, so let's just call it some number lambda. So I have the sum from j equals 1 to 6 of aij sj is some constant lambda that I don't know yet times si. That must hold for all I running from 1 to 6. Well, if I write that as a matrix vector equation, it's as equals lambda s. It's a set of equations to be solved for lambda and s. That's the eigenvector equation. S is going to be an eigenvector, and lambda is going to be the eigenvalue. So the eigenvector S will be a vector that records the strength of each team. So you may be thinking, this is easy. I just find the eigenvalues and eigenvectors of A. But then you might be thinking, hang on, this is a 6x6 matrix. It's going to have 6 eigenvalues and 6 different eigenvectors S. What am I going to do then? I've made it worse. I don't know which of the 6 answers to take. Here's where in an applied problem like this one, you have to remember any other conditions about the problem that you may have forgotten in your haste to make a mathematical formulation. And the hidden condition here is this one. The strengths all have to be greater than or equal to 0. Negative strength simply doesn't make sense in my model. Negative S would mean that a team is so bad that beating them actually makes me look worse. That just doesn't make sense. I could have a strength of 0. That would mean that a team, beating that team of strength 0 doesn't give me any information whatsoever about how good my team is. That could happen. But negative doesn't make sense. So I've actually got a hidden condition here. I've got the eigenvalue equation, and also I'm looking for solutions where each element of that vector S is greater than or equal to 0. There is actually a solution. Here it is here. Under this solution, team D is the strongest. And team A is next, and team E is third, which sort of makes sense if you read through the table. Team D has come out the strongest because although it didn't have a chance to play all the games, it did beat Team A and Team E, which otherwise were strong teams. So by beating two very otherwise strong teams, it's come out on top. Now, why did that work? Why was there an eigenvector? This is an eigenvector of that matrix with all non-negative entries. Well, here are all the eigenvalues. Actually, 4 of them were complex, but there is another real one down here. And here's the eigenvector of that other real eigenvalue. It's got some negative entries and some positive entries. If all the entries were negative, that would be okay, because any multiple of an eigenvector is also an eigenvector. I could multiply it by -1 and make it positive. But if I've got some positives and some negatives, I can't do that. And if you look along here in this example, there's only one eigenvector, it's this one, in which all the entries are positive. Now, that's just an example. Is it always going to work like that for all numbers of teams and all possible ways that the league could play out? Well, it turns out it is always going to work out. There's a theorem to the rescue. It's the Perron-Frobenius theorem. It says if you have a matrix with positive entries, then there is a unique eigenvalue such that all the entries in the eigenvector are positive. And that's the one we want. Now, that is a very powerful theorem. It applies to all matrices. It doesn't apply to our example because this theorem says the entries in A have to be positive. Now, some of my entries were 0, they weren't positive. There is a refined version of Perron-Frobenius theorem that also covers that case as well. So out of all n eigenvalues for a large matrix, only one of them has an eigenvector where all the entries are positive. That's the one I want. That's very useful. I've ranked the teams, and let's hope that settles the argument. Of course, in real life, that might not settle the arguments, but what happens in real life at the moment is, for example, with this American college basketball team, they ask sports journalists to rank the teams based on the results, and different newspapers hire different journalists, and they all come up with different results, so that's not very satisfactory. Also, this has been studied, and it turns out the journalists they rank teams highly if they have a lot of wins, even if those wins were all against weak teams. So they're overly influenced by large numbers of wins. So it would be a very interesting research project to look and see if any actual sports leagues in the world use this eigenvalue method, because to a mathematician, it looks like a very sound method. There's another thing going on here. How could you find that eigenvalue? Well, 6 by 6 matrix isn't so big. You could type it into MATLAB and find the eigenvalues and eigenvectors. But if you had a very large matrix, large numbers of teams, that would be very expensive, because you'd be looking for all the eigenvalues and all the eigenvectors and then throwing away almost all of that information. That would be a big waste. Turns out for an n by n matrix, to find all of them takes time n cubed. So for example, for a 1000 by 1000 matrix, 1000 cubed is 1 billion. That's already getting up to be a lot of work. 10,000 by 10,000, that is going to be a trillion. It's already impossible to calculate. We only need one eigenvector, just the one special one with the positive entries. And there is a way to get that. You can sort of motivate it the following. If I work out the matrix A times the vector with all ones, 1, 1, 1, 1, 1, that's just the number of wins of that team. You can see that. Let's go back to the beginning. Here's my result matrix. If I take this matrix times the vector with all ones, that's just the sum of the entries in that row. That's the number of wins. That would give me 3, 1, 2, 2, 3, 1, number of wins. Now what if I take matrix A times the vector containing the number of wins? Well, that would tell me 1 times the number of wins of team B plus 1 times the number of wins of team E plus 1 times the number of wins of team F in the first slot. That would be the number of wins, the sum of the number of wins of all the teams that team A has beaten. And you can continue like that. So A times 1 would be the number of wins. A times 1 would be the number of wins of the teams that you've beaten. AQ times 1 would be the number of teams that they've beaten, and so on. That's the basis of what is called the power method for finding an eigenvector. And that's much quicker. This only takes time n for an n by n matrix. This is practical even for extremely large matrices. So what have we got so far? Perron-Frobenius theorem, a fast algorithm for calculating the eigenvector, which is my vector of strengths of sports teams, and an important application. Well, you might think that ranking sports teams is not an important application, but this is the same algorithm that is used in the Google PageRank algorithm. The World Wide Web was introduced in 1993, and very soon the number of web pages became so large that you couldn't find them all by just linking from one page to the next. Search engines were introduced, but it was found that they returned a lot of irrelevant results, and it was then very hard to find the page you wanted amongst the list of results that returned. So the key idea that the founders of Google had, they were students at Stanford University, and they'd studied linear algebra carefully and paid attention to the Perron-Frobenius theorem. Their crucial idea was to assign a strength score, it's called the Google PageRank, to each web page, and to weight pages according to the number of links they received. Pages that were linked to a lot were considered to be more important, and they would come up higher in the search results. They calculated it using the power method that was just mentioned on the previous page. So now the matrix is very large, not thousands or millions or billions, but there are trillions and trillions of web pages. You never actually form that large matrix. It's completely impossible to store a large matrix with trillions of rows and columns. You just do calculations with it using the algorithms that you've developed. So now, hopefully it supports my argument, all of these things go together. A theorem that guarantees that everything's well posed and is going to lead to a sensible answer. An important application which is useful and led to the success of Google as a company. And a fast algorithm that makes everything actually practical in real life. Those are the ingredients, they all go together. And that is our first application of eigenvectors.